Welcome to our video about how to create your EM stimulating network with this equipment. We're going to start with the equipment and then we're going to go through the process of creating the stimulation and the RF signal. So, first piece of equipment we're going to talk about is the signal generator. This is where the signal that goes into the rest of the network starts. You can specify your amplitude, you can specify your frequency, and it has a lot of other tools, but those are the two main ones that we use. Next, the signal goes from the signal generator into the amplifier. This increases your amplitude and makes a stronger signal so that we can output more power into the medium. Very simple. This is an older amplifier. Very simple. Power, standby, operate. You push the power button. It takes a long time, but the standby button eventually lights up. That means it's warmed up and ready to go. And you can push the operate. That means start amplifying, and your gain knob is like a volume knob. It turns it up and down. So from there, it goes through the coax cable. We use RG8 cable. The signal generator is 50 ohms, our amplifier is 50 to 52 ohms. The cable is also 50 ohms or 52 ohms, and it's important that it all matches so that most of the signals can go out. So it goes through our coax cable, our N-type connectors, into our dual directional coupler. The dual directional coupler is used to measure the forward and reflected power going through our network. So the forward power would be the amount of power that's coming out of the amplifier towards the antenna, and the reflected power is the amount that's reflected back from our matching network and antenna. If we do not have 50 ohm impedance in our antenna and matching network, we have the majority of our signal is reflected. So then we go through another RG8 cable into our matching network. The matching network consists of two variable capacitors. The one is in series and one is in parallel with the power going to the antenna. And they are encased in this aluminum box called Bud Box, which encases the E&M waves from penetrating in and coming out. Then we have another N-type connector, which is connected to an RG8 cable, which is our antenna. Our simple coax antenna is just 7 centimeters of the shielding from the outside of the RG8 cable stripped away so the center conductor can emit the frequency. And normally this box is full of water. And that's important, but you will have to learn about that on your own. So, now we know the pieces of our network. One more important piece of equipment. We have a network analyzer. This network analyzer is very important and very nice piece of equipment. It tells us what the network consists of. It tells us what the impedance of the network is at different frequencies, and so we can match our network and create a network that is 50 ohms, and so we emit as much of the power as we can. I'm not going to teach you electromagnetics, so you're going to have to learn that on your own, but I'm going to show you how to use this equipment. So first we start by hooking up our equipment. We have the cable, coax cable, coming from the signal generator into the amplifier. Pretty easy. This says RF output. This says input. If you don't, that should be pretty straightforward. And this is a smaller cable. Not important. It is a 50 ohm cable, but it doesn't have to be super large. Here we have our output, and it goes into the RG8 cable, and it goes into the dual directional coupler. From the dual directional coupler, we have another coax cable that can be either hooked up to the forward or reflected to measure the signal going in each direction. That signal goes up here to our spectrum analyzer. The spectrum analyzer can measure all sorts of different types of signals, but what we're interested in is what is coming on this cable, which relates to what is going through the network in each direction. We'll show you how to read that later. And from the dual directional coupler, goes into our matching network box, goes into our antenna. So, how do we know how to tune the network and get it to 50 ohms? Well, that's what our network analyzer is for. So we pull our network analyzer up, and we know the cable is 50 ohms, and we know the amplifier is 50 ohms, we know the spectrum analyzer is 50 ohms, or the signal generator is 50 ohms, but how do we know what our antenna and our matching network are? We don't. That's why we have the variable capacitors, so we can tune the network to be 50 ohms. So, first things first, hook up the network and hook it up to the network analyzer. And across here we can see this is our gain in dB, decibels that is, and this is our frequency along this axis. So if we see this peak right here, it relates to 99 megahertz here. And as we turn the variable capacitors here, like this, both are variable, we can look back at the network analyzer and we can see that changes the impedance of the network. So right here we have 156 ohms, or 156 megahertz, and if this network is close to 50 ohms, our reflection will get very negative. So that means a very small portion of the of the signal is being reflected. So we want this spike as low as it can be. One of the other ways to look at this would be in a Smith chart format, and if we look at that, we can see the impedance as measured by the network analyzer, and the other axis is the frequency, but it's a circular axis. So as the frequency changes, the impedance of the network changes. So most of the time the impedance is out here. So 50 ohms is right in the middle, and it goes all over and has a lot of imaginary and real parts. Again, I'm not going to get into that. It's not important for the use, but if you are operating this, you should look into it. We're going to go back into log mag because this often is the easiest way to match it. So there's a lot of variables, and we don't have water in our box, which makes it difficult, but let's just say that we want this as negative as possible. So we're looking at 156 megahertz, and we have our negative 25 dB reflection. So we are done with this. We can disconnect and hook this back up to the amplifier. A note on the network analyzer. So when we had our network hooked up to our network analyzer and we were measuring the signal, we wanted the most negative dB value. So what we were measuring at that point was through port 1 we were measuring S11, which is the amount of the signal leaving port 1 that is coming back to port 1. So a negative dB value would mean that a minimal amount of the signal that is going out of port 1 is coming back to port 1, and that is what we want, because when it's coming out of the amplifier, we want all of the signal being emitted by the antenna and not being reflected back. So we find a configuration for the network and the antenna so that we can get the maximum power out. And make sure all these connections are good and tight. Don't cross thread them, but just make sure they're good and tight. And so now we matched for 156 megahertz, right? We hit frequency, 156 megahertz. We're at 156 megahertz. Our amplitude is 0 dBm. We do not want to exceed 0 dBm emitted from the signal generator. 0 dBm relates to 1 milliwatt. The amplifier is designed to take 1 milliwatt of input. If you increase this, you can risk damaging the amplifier. We do not want to damage the amplifier, so we use 1 milliwatt coming from the signal generator. So we make sure the gain's down. We have 156 megahertz being emitted here, 0 amplitude. We can start turning this on. And to start, we want to hook up the spectrum analyzer to the forward port in the dual directional coupler. So we'll wait a minute and wait for this to warm up, and the standby light will be on. And a nice little warning here, do not input more than 0. Moving back over here, you can see that our amplifier is all warmed up, our power button is on, our gain is all the way down, and our standby light is on. That means that there's very little signal coming out. We can turn the RF on. First, let's go up here to our spectrum analyzer. This is one spectrum analyzer we use, another one is down over here. They have very similar functions made by the same people. They have frequency, amplitude, and span, and their options. It's a pretty user-friendly piece of equipment. This one's normally in the lab. This is the one that's going to be used right now. So, things that we're going to set. We know that our output from our signal generator and the signal that we are caring about is 156 megahertz. So we're going to do our start frequency. We're going to do a larger span, so I'm going to start 50 megahertz. And we're going to do our stop frequency as, let's say, 300 megahertz. So if you come down here, we're not amplifying yet, but we can turn with the RF off on button. We can turn our RF on, and we look here and you see a little spike. That is our signal bleeding through the amplifier and coming through. So you go over here and we can do peak search. Hit peak search, and it puts a little diamond on top of the peak, and it gives us our signal value. So we have our frequency, 156.2 megahertz, and our signal value is negative 47 dBm. This is dBm, not dB, so it is an actual power value, milledecibel versus dBm, which is just a relative power value. So you see our signal here. We come down here. We're not going to emit a strong signal. We're going to start at about 0 watts, or, well, no, we're going to start at about 10 watts. So 0 dBm on this because I know what all the values are. But we hit operate, and now you can see that it went from negative 46 dBm to negative 8 dBm, and that's our signal. So you can see a much larger spike. And if we concentrate on this again and we turn the gain knob down here, turn that just a little bit, and we can see that these numbers can increase or decrease, and you can concentrate on the spike going up and down with the turn of the gain knob. That is how we adjust our power that is coming into our system. So we want to get a ideal more than negative 15 dBm match. So we set this pretty near 0 dBm, and we come down here along our coax back to our dual directional coupler. Remember, we're looking at the forward power. Now we're going to hook it up and measure the reflected power. We want to have 15 dBm difference, or 15 dB difference between these two. That means that the majority of the signal is going through and not being reflected back. But we see now we're only at about 10. So we can come over here and we turn these little knobs back and forth, and we can improve that. See how it decreases? Yeah, so that's not too bad. As long as we're more than 15 dB difference, we're doing well. And that's all achieved by changing these variable capacitors. So we have our network matched fairly well. That means that most of the signal is coming out of here. For each frequency, the attenuation of the dual directional coupler is different. So you must check the attenuation of the dual directional coupler. The easiest way to do that is hook up the cable directly to the signal generator. You know how much power is coming out of here. You can know how much is being picked up here. That tells you your attenuation at that frequency. But it's important to measure for your calculations later so you can know what exact power that this power reading from the signal generator relates to from the amplifier. So that's something you need to check at every frequency. But now we have our negative 15 dB difference, and our power is going forward. It's coming out of the amplifier through the dual directional coupler into the matching network through the antenna. And right now this antenna's emitting like crazy because we don't have water around it to insulate it. So all good fun. We really should have the door to the Faraday cage over it, and so that would protect us if there wasn't water around that. Other notes: we do not want more than 1 watt being reflected back to the amplifier. If you can maximize the reflection as being less than 1 watt, you're doing well. There's a little bit of give, but we don't want 10 watts in here because that'll blow this up. So a good rule of thumb is if the reflection is more than 10 dBm, then you have too much reflection. So if you're pushing 5 dBm forward and you have 15 dB difference, that means that this is at negative 10 dBm. That means you have about a watt coming in. And that's a good maximum to strive for. So if you can do that, you have a good match, you have good power coming out of your antenna, and you're protecting your equipment. So hopefully this has told you everything you need to know to create your RF network and start your tests. Good luck.